Hi students and friends, welcome to the channel Learn and Teach by Ayaz. So I was doing CIE 5070 past paper and I'm done with question number 1 till 4 for winter 2022 and the variant was 42. So let's continue our video lesson. Here's a question number 5. Solution K is dilute sulfuric acid H2SO4. A student determines the concentration of solution K using a method that involves titration. Student measures 20 centimeter cube of solution K using a pipette. Student makes up the solution to 250 centimeter cube with distilled water. This is solution L. Name another piece of apparatus that could be used instead of a pipette to accurately measure 20 centimeter cube of solution K. Spirit. Both burette and pipette has higher accuracy. So I will write burette here. B. Name the container in which solution L is made. Standard flask or volumetric flask? C. A pipette is used to transfer 25 centimeter cube of solution L into a conical flask. Name the other piece of apparatus that is used with the pipette. Now it's important, we have to use the bulb with pipette. This is the shape of the pipette. And use bulb, it's also known as pipette filler. D. Student adds 3 drops of methyl orange to solution L in the conical flask and then places the flask on a white tile. Student fills a burette with 0.1 mole per dm cube potassium hydroxide KOH aqueous. The KOH aqueous is added to the flask until there is a change in color, the color change. Number 1, state which liquid should be used to wash out the burette before filling the burette with KOH for use in the titration. Definitely it must be aqueous potassium hydroxide. So you write KOH aqueous. Number 2, explain why the conical flask is placed on a white tile. You see the color change clearly. You see the color change. The color change is actually the indicator. Number 3, state the color change of the methyl orange indicator at the end point. The color changes from dash to dash. So initially it's added to alkali, then we have added, it's added to acid, then we have added potassium hydroxide, which is alkali from burette. So acid to alkali. So in acidic medium, the color will be red, and in alkaline medium, it will turn to orange. E. The student does 3 titrations. Diagrams below show parts of the burette with the liquid levels, both at the beginning and at the end of each titration. So here's the result. We need to use these diagrams will be used to complete the following table. So for number 1, we have final burette reading. If you look at this, 24.12, 24.2 centimeter cube. What about the initial reading? It's 0, so you'll write 0 here. The volume added will be 24.2 because final minus initial will gives you 24.2. For second titration, the final burette reading will be 46.1, 2, 3, 4, 5. 46.5. What about the initial reading? 25.12. 25.2. So if you will subtract 25.2 from 46.5, we will get 21.3. For third titration, okay, coming back to this titration number 2, first of all, we need to calculate the difference I'm already done with this. For the third titration, the final bureau reading will be 32.32, 1, 2, 2, 3, 4, 5, 6, 7. So 32.7 will be the final bureau reading. Initial reading will be 11.2. So let's see the difference between these two. 32 minus 7, 0.7 minus 11.2. 7 minus 2 will be 5. 2 minus 1 will be 1. 3 minus 1 will be 21. 21.5. Which of these will be best titration results? It must be 21.3 and 21.5. The reason is that 24.2 is much higher than these two values. These two values are closer to each other also. So we'll take these two as best titration results. Take the best titration results in the table. Use our titration results to calculate the average volume of KOH. So what we will do, we will add these two, 21.3 plus 21.5 and divide it by 2. What we will get? We will get 21.4 centimeter cube. F. Calculate the number of moles of KOH in the average volume of 0.1 mole per dm cube KOH used. So 0.1 mole per dm cube means 1000 centimeter cube contains 0.1 mole. Therefore, 21.4 centimeter cube contains X moles. So X will be equal to 0.1 multiplied by 21.4 divided by 1000. So 0.1 multiplied by 21.4 divided by 1000. We'll get 2.14 into 10 raised to the power minus 3 is the final answer. The equation for the reaction of potassium hydroxide with sulfuric acid is shown. This is the reaction. 2KOH plus H2SO4 gives K2SO4 plus 2H2O. Use this equation to calculate the number of moles of H2SO4 in 25 centimeter cube of solution L. So KOH and H2SO4 according to the equation. 1 mole reacts with, 2 moles reacts with 1 mole. Therefore, 2.14 into 10 raised to the power minus 3 reacts with X mole. So X becomes equal to 2.14 multiplied by 10 raised to the power minus 3 divided by 2. 0.00214 divided by 2. We'll get 1.07 into 10 raised to the power minus 3. Calculate the number of moles of H2SO4 in 25 centimeter cube of solution N. We have already calculated the number of moles in 25 centimeter cube. So you will write 25 centimeter cube contains 1.07 into 10 raised to the power minus 3. Therefore, 250 centimeter cube contains X moles. So X becomes equal to 250 multiplied by 1.07 into 10 raised to the power minus 3 divided by 25. 110. So you will multiply 10 by 1.07 into 10 raised to the power minus 3. You will get 1.07 into 10 raised to the power minus 2. Or you can write 0.0107. Deduce the number of moles of H2SO4 in 20 centimeter cube of solution K. So it must be same because 20 centimeter cube of solution is added to 250 centimeter cube. So the number of moles will be same, 0.0107. Calculate the concentration of solution K in mole per dm cube. These moles are in 20 centimeter cube. So 20 centimeter cube contains 0.0107 moles. Therefore, 1000 centimeter cube contains X moles. So X equals to 1000 multiply by 0.0107 and divided by 20. 1000 multiply by 0.0107 divided by 20. 0.535 moles per dm3. Okay, a student does the same experiment using 30 drops of methyl orange instead of 3 drops of methyl orange. Methyl orange is acidic. State if the average titration volume of KOH is smaller, larger, or unchanged when 30 drops of methyl orange are used. KOH is alkali, and we are adding alkali to acid. So if the indicator is acidic, so it will definitely neutralize some of the alkali. So the volume will be larger because the concentration of the acid increases. More acids added to the conical flask. Therefore, higher volume will be required. More QH required to neutralize. Question number 6. Student is provided with aqueous copper 2 chloride, aqueous zinc sulfate, and an aqueous solution labeled X. Student tests the 3 solutions by adding each reagent shown in the table. A. Complete the table with the expected observations. So the reagent is aqueous sodium hydroxide, and for copper 2 chloride, we will get blue precipitate, and in excess of aqueous sodium hydroxide, these will remain or insoluble. In case of zinc sulfate, we get white precipitate, and it's soluble in excess, so you will write soluble here. For X, we'll get green precipitate and precipitate remains. Recall green precipitates are either of Fe plus 2 or Cr plus 3, but here it remains, which means it's insoluble. So it must be of Fe plus 2. Aqueous ammonia, for copper 2 chloride, again you'll get blue precipitate, and in excess of aqueous ammonia, we'll get deep blue solution. In case of zinc sulfate, we'll get white precipitate, and we will get colorless solution. In case of X, we'll get green precipitate, and the precipitate again remains because these are of Fe plus 2. By the way, for Cr3 plus, precipitate also remains. It does not dissolve in excess of aqueous ammonia. Aqueous silver nitrate and dilute nitric acid. Silver nitrate is the test for the chloride ion, so here we'll get white precipitate. And in case of zinc sulfate, no reaction or no change. In case of X, they have mentioned yellow precipitate. Yellow precipitate are of I negative, so there must be iodide ion. Aqueous barium nitrate and dilute nitric acid. Barium nitrate is a test for the sulfate ion. So we will get white precipitate for zinc sulfate only. In case of copper 2 chloride, we'll get no change. For X, we have also mentioned no change, so sulfate ion is absent here. Sulfate ion absent. Now they are asking about the identity of X. You can write iron 2 chloride FeI2 or iron 2 iodide. Number 7, when alcohols burn, they release heat. Student uses the apparatus shown to investigate the amount of heat released when the 5 different alcohols burn. So here's the setup. We have thermometer, we have metal container, we have 200 centimeter cube of water. We have burner containing alcohol. Student determines the temperature rise of 200 centimeter cube of water when an alcohol burns. Student repeats the experiment using the same amount of each alcohol. Now, number of carbon atoms: 2, 3, 4, 5, 6. And see the temperature change. For 2, we have 25 degrees centigrade rise. For 3, we have 46 degrees centigrade rise. For 4, we have 53 degrees centigrade rise. For 5, we have 67 degrees centigrade rise. For 6, we have 81 degree centigrade rise in temperature. Now the next part, what they are saying. A, plot the results on the grid. Circle the anomalous point on the grid. Draw a straight line of best fit. So for your convenience, I'm going to show the values here. So it will be easier to understand how I'm getting this graph. I'm writing the values for each carbonate. Start from 2. We have 2, 3, 4, 5, and 6. So we have 25 for 2 carbon atom, 46 for 3, 53 for 4, 67 for 5, and 81 for 6. These are the values. Now it will be easier for us to draw the graph. For 2 carbon, it must be 25. So we'll get the spot here, somewhere here. First spot, dot. For 3, 46. So we must get here. For 4, 53. (48), 50, 53 must be here. Okay, now for 4, for 5 we get we must have 67 degrees centigrade rise in temperature. So it must be here. For 6, the temperature rise is 81. So it must be here. Draw straight line of best fit. Extend the line of best fit on your graph. I'm done it. So I'm extending this line. Use the extended line to reduce the expected temperature rise if an alcohol with 7 carbon atoms used in the experiment. So let's calculate for the 7 carbon. So it must be above 90, here 80, 82, 84, 86, 88, 90, and It's like around 92 degrees centigrade. So if you look at this graph carefully, it must be like between 92 to 96 degree. So this is a spot going like this. The initial temperature of the water is 15 degrees centigrade. Explain why this means it is not possible for the student to obtain the temperature rise in B1. Because the boiling point of water is 100 degrees centigrade. Boiling point of water is 100 degree centigrade. So final temperature will be above 100 degrees centigrade. So it's not possible for the student to obtain the temperature rise. Number 3, it suggests one change that can be made to the experiment that would make it possible to obtain the temperature rise in B1. You can use ice or water below 4 degrees centigrade. Thanks for watching. Press like and share my videos. Keep comments. For more videos, subscribe to my channel and press the bell icon.